midway recording. Please thanks for coming, because otherwise I would have spent 1 hour talking with myself. Okay, now everything's good. So let's go back to the canny edge detection. It's based on 3 objectives. So basically finding a low error rate, finding the points that should be well localized, and get the single edge response, meaning that the detector should return only 1 point for each true edge. And the idea of Kenny was to make these 3 objectives mathematically sound. So basically, what Kenny did was the approximation to the optimal edge detector using the first derivative of a Gaussian, smoothing the image with a circular 2D Gaussian function, compute the gradient as a result, and use the gradient magnitude and direction to estimate edge strength and direction at every point. And that's what we've done at the first half of this lecture. But this may generate a wide broken edges as a result. So basically, what the solution of that Kenny gave was to use this idea of no maximal suppression. So basically, what no maximal suppression is, it's going to follow the main direction, follow the direction of the edges. It's going to get rid of lower values, of lower intensity values. Lower intensity values of what? Of this image that was the result of applying a smoothing function and then a gradient function. And that's what it meant. That's what no maximal suppression is. Going to find the main direction, suppressing the lowest signals from this direction, and just keeping the maximal signals. Signals meaning the maximum value, intensity values. And a third bit is the edge detection by using this double thresholding method. Let's see how it goes. So, well, we've seen all this Gaussian convolution kernel to get the smoother function, smoother image. A gradient kernel to find where the changes are. You get the magnitude and orientation of the gradient. Why do you need magnitude and orientation of the gradient? Well, the magnitude you're going to use to find where the edges are. And the orientation you're going to use to find where to follow the edges, because the edges will always be orthogonal to the direction of the maximal change of the gradient, right? And there comes this idea of no maxima suppression. So you see the result of applying these steps here will be something like this. So you see that the edge is here, but there's also some kind of, I wouldn't say noise, but it's breaking the idea of having very thin edges. So basically, what I want to do is to follow this. Right? You can see that there's clearly an edge here. But here you don't really know which way to do it. Oh, that's fine. Forget about this. Follow this. We're going to decide it later. So that's basically what no maximum suppression is. Right? So it's going to keep the largest signals along what? Along the orthogonal direction of the gradient. So you see that the gradient's probably point is pointing in this direction. So you're going to follow what? You're going to follow your orthogonal direction. That's the direction of the edge. Clear? Okay. So that's basically it. And also, I don't allow any gradient orientation. You see that a gradient is just a subtraction of peak values. So you may take any value. So basically, it's a digital image. So I don't need any value. I don't want to have any values on it. So basically, I discretize, just allowing values within 45 degrees interval. So if any value of the gradient falls in this interval, I say that you will have a 45 degree. If it follows here, it's going to have 100 and we'll have the value of this angle here. That's between 155 and minus 155, and so on. So basically, it's a segmentation of the gradient value. And we need to two things. Once I have this potential edge, but also have false edges that's been selected from other portions of the image. So I want to get rid of that. And how do I get rid of that? By using a threshold. So basically, all values below a threshold I change to 0. But selecting a good threshold is very difficult. And some false edges will still remain if t is too low, and some true edges will disappear if t is too high. Right? So what do? We keep two thresholds. One that's gonna get anything that's below one low threshold that's gonna get anything that's below a certain threshold, even though keeping some false edges, and anything that's too high that's gonna basically filter these false edges and get some of the real edges, but we'll have some of the edges that will disappear from that. So what do? That's very simple. I basically fiddle around with these two thresholds. So basically, I have one threshold that's T1, that's a low threshold, and I get a threshold T2 with a higher threshold, basically twice T1. What do I get? Is two images in the output. The image from T2 will contain fewer edges, but it has gaps in the contours. And the image from T1 will have many false edges. I combine the images from these two images, T1 and T2. And basically, I link the edges from T2, from the stronger threshold, into contours given pixels from T1. I'm basically going to follow the edges on the image T2 with the threshold T2. And whenever there is a gap, I'm going to look at T1 if there are pixels in that gap. That's basically what happens. So you see that if I follow the strongest threshold, we're going to have this gap there. Remember that I pointed to these gaps. So, but on T1, we're going to have some spurious edges here. But I don't care about the spurious edges. I just care about the values that are in this path. In this path given by T2. Well, there are pixels in this path on T1, so I just fill them. I just get this one and get a 1 here. There's another one, I get a 1 here. So basically, the idea is link, search for the 3x3 neighborhood of each pixel and connect the pixel at the center with one having the greater value. Searching in the direction of the edge, in the direction of the gradient. Is that clear? Yeah, so I know that the first time that I read the Kenny edge detector, I got a little bit confused, but it's basically what we've seen so far is smoothing plus gradient, and then with some very smart heuristics to fill up the edges. That's a very powerful technique. So we have the original image here. That's the result of the gradient of this smoothed image. That's basically this. So you smooth this image and get a gradient. That's the result of the Marr-Hildreth algorithm, and that's the result of the Kenny algorithm. So unfortunately, that's another example where the images, the digital images in the book, are not as good as the printed image. So this is one I had to scan from my book, because basically in the digital version of the book, this image is just the same as this image. There's basically no difference at all. Whereas in the book, you can clearly see that the Marr-Hildreth lost some pieces of these edges here, whereas the Kenny got it all, because it has those algorithms for filling up gaps in edges by following edges and filling up gaps. So again, this is the threshold, the threshold, the gradients of this smoothed image. This is the result of Marr-Hildreth algorithm, and this is the image obtained by the Kenny algorithm. And then again, it depends on what you want to do with this image. If you want just a better model of this image with the edges, I'd say that this one is a lot clearer, even though you have some thick edges here. So you can't. It is not properly segmented. Instead of having edges here, I have a region, and I have regions here. Whereas here is a little bit broken, but I don't have anything that's region. So I have everything that's a kind of a proper contour. Whereas the mass hue is more or less the same thing, but it has more gaps around this whole thing. Okay, right. So, and the final algorithm that I want to talk with you today is the half transform. Okay, so none of the other algorithms so far takes into account the shapes of the curves where the pixels lie. So if I have a ball here and part of the ball is occluded by some reason, so probably under shadow or something here. This is not a proper segmentation of the ball. This is not a proper segment. This is not a ball at all. Like 2/4 of a ball, 2/3 of a ball. There's this bit missing. But we clearly see that there could be a contour here. So why don't we use the equation of a circle to be able to segment this properly? That's exactly what the half transform does. It takes into account the shapes of the curves where the pixels lie. Then once detected, this curves from the edges of the region boundaries of interest, and it segments objects according to the known shapes. It can be used to segment straight line, circle, or any parameterized curve. In particular, this guy here gives a wonderful explanation of the half transform. That's on the Coursera image processing course, right? And this image was taken from that. Oops. So basically, what we have. So let's see if I have a straight line. The equation of a straight line in polar coordinates is this, right? So ρ is equal to x cosine theta plus y sin theta. So this is the equation of a straight line. Take a point given by the edge detector. Then for every point that passes, that passes an infinite number of straight lines. Each of these straight lines has its own parameter ρ and theta, right? So what do? They decide by voting. So every point adds a vote to a particular number of ρ and w pair for a series of lines. Then every line gets a vote. Multiple points in a line. Obviously, if I have multiple points in a line, so for instance, this point, I have 1 point here, 1 point there, 1 point there, 1 point there. Every one of these points will be will lie on this line, and this same line will have the same parameters ρ and theta, right? ρ and theta. So what do? I just get the line with a larger number of points. That's the half transform. So basically, I get all the points that I found in the image and see check if they on the parameter space, get the ρ and theta, and fill up how many votes each one of these ρ and theta get. And basically, I get the most voted bin of this whole phi plane, and those are the ones that I'm going to use to segment. So basically, votes are accumulated in this whole theta space. You add votes to these accumulator cells. These are called accumulator cells for every point. Find the maxima in the accumulator. There may be multiple if there are multiple lines through each point. That's fine. find the whole theta where many points lie, and then you can basically reconstruct a figure like this. You can fill up that, right? Because this figure, now we are not talking about a straight line, but we're talking about a equation of a circle. A particular equation of a circle will receive quite a number of votes in the parameter space. So this will be a more complex parameter space. So basically, this number of votes will be the number of votes on top of what? On top of one single equation for a circle. So in order to segment, I just get the best voted one, and then I use the equation at basically I can calculate this center easily and the radius easily, right? Then I can segment by fitting a circle into the image that I want to segment. So that's all there is to the rough transform. So basically you do an edge detection from an image. Every point is defined an equation like, so for straight lines will be an equation like this. And every point detected places a vote in the accumulator space rho and theta. You find the maxima in the accumulated votes, and that's all this. That's all there is. The attractiveness of the rough transform arises from subdividing the whole theta space into accumulator cells. So this is one example of the application of the whole theta. So basically, the first thing that I do is I do an edge map that you could use, for instance, the Canny algorithm for doing this, for obtaining that. Then for every edge map, so I don't know if this point falls in this line or in that straight line. So I just see how many lines, how many points, how this scores, given the number of points that I have. And this is the parameter space. This is the whole theta parameter space. This algorithm then finds the maxima here and there. Which are basically what? These 2 points have a single parameter theta and a single parameter rho. There are parameters for 2 edges, 2 straight lines. So I basically reconstruct the straight lines given these parameters that I found by voting, that the algorithm found by voting, and then superimpose it on the image, and I know exactly where this is an airport, exactly where the airport is. Okay, any questions? So rough transform for circles, the same thing by using the circle equation. That's x minus x0 squared plus y minus y0 squared equals to the radius, the squared radius. You need to find then it's a little more complex. It's not, you don't have 2 parameters, you have 3 parameters, x0 and y0 and r. And we're going to have a 3D accumulator space. And basically, the rough transform works for any parametric curve. The more parameters, obviously, the more expensive the curve is. The vector space takes a lot of space, a lot of memory, and that's basically it what I had for you today. We are at exactly the very middle of this lecture, so I'll keep on talking about segmentation next week because basically these 3 chapters that we are in now, they are not only the most complex, but they are also the ones that have the largest variety of applications. Right, so I'll stop here today's lecture. If you have any questions, please feel free to ask me or to send an email. And oh, by the way, the Canny algorithm and the half transform, they are all simple functions in the OpenCV. And I think next Monday I'm going to show you some examples of application of the Canny and the half transform. They are very easy to apply. They may not be, as I said at the beginning of the course, it's very simple to present these functions as black box functions. You just get the function and apply it and see what you get as a result. That's what most of the courses that you get on the internet, that's what they do. So you have this function here, you apply this image and you get that. And then you don't know why they don't work. You will only be able to understand when they don't work if you really understand the theory. And please have a look at the Canny and the half transform this week, because these are two key algorithms for that. Well, the other stuff, the things that I presented at the beginning of the lecture, you know them all, right? So you don't need to look at them anymore, because basically blurring, Gaussian blurring, applying the Laplacian convolution, it's just a combination of these two. But the Canny and the half transform here stuff. So if you have 1 hour to dedicate to this topic this week, read more about Canny and half transform. So no question came out, and that's basically it. Thank you, and I'll stop recording now.